Welcome to the Intel FPGA training, Debugging with the Ethernet Toolkit. My name is Marlon Price, and I'm going to be the instructor for this session. By the end of the class, you will be able to describe the purpose, features, and functionality of the Intel Quartus Prime Pro software's debugging tool, the Ethernet Toolkit. And you'll be able to set up and use the Ethernet Toolkit to analyze and debug your Ethernet IP cores while connected to a live link in system. In this course, we will start with an introduction to the Ethernet Toolkit. Then, we will look at the collection of Intel FPGA Ethernet IP cores supported by the tool. After that, we'll see how you can enable the support for the Ethernet Toolkit in your Intel FPGA design. And finally, we'll go over some of the information you can get from the IP core during an Ethernet Toolkit session by studying its user interface. So let's begin with an introduction to the Ethernet Toolkit. The Ethernet Toolkit, simply put, is Intel FPGA's on-chip debugging tool for viewing real-time status information of Ethernet Intel FPGA IP cores while running in a target FPGA. This visibility into the IP core can be absolutely crucial if you're trying to figure out why a link is not functioning or behaving as it should or as you expect. Is there a problem with your reference clock? Is it a protocol implementation issue? Has your IP core been configured the way you expected? Is your application communicating with the IP core correctly? Has your partner device done an illegal operation, or are you receiving poorly formed packets? Is your transmission medium broken or extremely noisy? How much work is your FEC block doing to correct for errors? The answer to any one of these questions could determine the reason for the link not working. And trying to figure this out without visibility into the IP core can be very challenging or become very expensive. The Ethernet Toolkit runs on the Quartus Prime Pro software's system console, so it is built on a proven technology platform. It uses your FPGA's existing JTAG connection to communicate with the IP core, so no additional I/O or board components are needed. It works by monitoring the IP core's register space for information, so you do not need to know the register addresses and bit fields, and the tool is programmed to interpret this information for you. The gathered information is then displayed to you using an easy-to-use graphical interface. It also allows you to write to registers to change core settings and to enable and disable core features. This diagram shows how the Ethernet Toolkit works and gets connected. As you can see on the left, the Ethernet Toolkit is running on a host PC and gets connected via the JTAG cable to the FPGA, the same JTAG connection you would use to program the FPGA during development and to run tools like the Signal Tap Logic Analyzer. Through the JTAG IP, the toolkit connects to the Ethernet IP and monitors it while it runs in the FPGA, exchanging packets with the system. There are several advantages of using the Ethernet Toolkit over other solutions for debugging your Ethernet link. First, the information displayed is real-time, coming from an active link. This lets you diagnose issues as they occur versus performing captures and analyses separately. The Ethernet Toolkit decodes the register addresses and content for you. Unlike other low-level debugging tools, you do not need to know the locations of specific registers and bit fields, and you do not need to manually interpret data read from and written to the IP registers. The tool is lightweight, so its impact on your total resource counts and performance are minimal. The only hardware you need is the same JTAG cable you use for programming and debugging already. The Ethernet Toolkit graphical user interface is easy to use, being similar to other Quartus debugging solutions and toolkits. And finally, it comes for free with your Quartus Prime Pro installation. So what can you do with it? Using the Ethernet Toolkit, You can do things like verify the current status of the link, reset the entire IP or select layers of the IP, read select IP status registers, read and write to the IP configuration registers, and read the statistics registers. When you generate the example design for your Ethernet IP core, its registers are also exposed to the toolkit. This means that additional features and functionality in the example design can also be controlled by the toolkit. With the example design, you can enable and disable the example design's packet generator. You can launch predefined testing procedures. You can enable and disable direct MAC loopback. You can program specific source and destination addresses. Again, this added functionality requires the use of the example design in your hardware. Before we get any further, it is worth mentioning the Ethernet Link Inspector. The Ethernet Link Inspector served as sort of the predecessor to the Ethernet Toolkit. If you are familiar with the Ethernet Link Inspector, we just want to take a second to highlight the similarities and differences. When it comes to interacting with the Ethernet IP core, both the Ethernet Toolkit and the Ethernet Link Inspector use JTAG to access the core registers to provide status information along with some control. So in this way, they are the same. But whereas the Ethernet Link Inspector was a script file that you downloaded from the web and opened in the system console, the Ethernet Toolkit is integrated into the system console platform. This provides some nice advantages over the Ethernet Link Inspector. For toolkit operation, highlighted in row 2 of this table, the Ethernet Toolkit can automate some operations like the detection of the IP and its configuration. It also means the usage flow and UI features are more similar to other toolkits also built into the system console, giving a more uniform look and operation. For user experience, integrating into the system console means performance advantages like faster loading and better usability. It is not noted on this slide, but you should be aware that specific IP cores may have some additional differences between the Ethernet Toolkit and the Ethernet Link Inspector. But check the device, IP, and Quartus version to see which debugging tool you have access to and to see exactly what is supported. In some cases, you can choose which one you want to use. In our next section, we will see which FPGAs and Ethernet IP support the Ethernet Toolkit. For Stratix 10 FPGAs, the Ethernet Toolkit is currently supported by selected IP targeting the L-tile, H-tile, and E-tile. For the L-tile and H-tile, the 10G base KR, low latency 40 gig, and low latency 100 gig Ethernet IP support the Ethernet Toolkit. In addition, the H-tile hard IP for Ethernet IP core supports the Ethernet Toolkit. This IP core configures the hardened 100 gig MAC, PCS, and PHY found in the H-tile. For the E-tile, the low latency E-tile 40 gig and E-tile hard IP for Ethernet IP support the Ethernet Toolkit. The E-tile hard IP supports 10 gig, 25 gig, and 100 gig configurations, all of which can be used with the Ethernet Toolkit. Lastly, for ASIC prototyping in the Stratix 10 GX 10 million cell device, the low latency 40 gig for ASIC Proto IP also provides toolkit support. Note the last two columns in the table indicate the Quartus and IP versions providing initial support. For Agilex FPGAs, the Ethernet Toolkit is currently supported by select IP targeting the H-tiles and E-tiles. For the H-tile, the low latency 100 gig Ethernet IP and the H-tile hard IP for Ethernet IP cores support the Ethernet Toolkit. Like with Stratix 10 devices, the H-tile hard IP configures a hardened 100 gig interface in the tile. For the E-tile, the low latency E-tile 40 gig and E-tile hard IP for Ethernet IP support the Ethernet Toolkit. The eTile Hard IP supports 10 gig, 25 gig, and 100 gig configurations, again, all of which can be used with the Ethernet Toolkit. As Ethernet Toolkit development is ongoing, the plan is for additional IP and newer tiles to potentially also have Ethernet Toolkit support. So always check with the latest documentation to see if your particular target device, IP core, and tile are supported. Now you have an idea of the Ethernet Toolkit and whether it is supported in your core. Now let's see how to enable it in a design. The Ethernet Toolkit flow involves two main steps: setting up the Ethernet Toolkit, making it available for you to use, and then launching it. To set up the Ethernet Toolkit, you must enable the JTAG to Avalon bridge in your IP settings. Then you can generate the example design if you plan to use it in your development. Next, you compile your Quartus project and configure the FPGA with the resulting configuration file. The project you compile will either be your original design with the bridge enabled or the example design generated by the IP parameter editor. Enabling the JTAG to Avalon bridge is an option in your Ethernet IP parameter editor. It is typically found at the bottom or near the bottom of the first or IP tab. Turning on this option tells Quartus to synthesize the logic necessary to convert commands sent over JTAG into memory mapped requests and to convert responses from those requests back into JTAG. This, of course, allows the toolkit to interact with the IP blocks and access the registers. This option eliminates any need for you to make manual connections in your design files. When you are configuring your Ethernet IP core, one of the tabs available in the parameter editor window is the Example Design tab. The tab allows you to create an example design containing your configuration of the Ethernet IP. This example design can be compiled, simulated, and programmed into a target development kit for hardware testing and verification. To generate the example design, configure your core options and features. Go to the Example Design tab, choose Simulation versus Synthesis or both, select the design language and the target development kit. If your development kit is not listed, then the tool will still generate an example design, but you would be responsible for setting the right part number and pinouts. Finally, click on the Generate Example Design button at the top of the window. Once the device is programmed, you are ready to launch the Ethernet Toolkit. There are 4 basic steps to do this, and while they're listed on this slide, let's go through them in a bit more detail. First, you launch the System Console or System Debugging Toolkits from the Quartus UI. These options can both be found in the Tools menu under the System Debugging Tools submenu. For step 2, you want to load the design. Loading the design involves opening your Intel Quartus Prime software project or programming file within the System Console platform. This essentially tells the software the programming file loaded in the FPGA. To do this, click on the Load Project button in the Toolkit Explorer. After loading the project, the Instances and References column should display information about the design, such as the design name and the blocks within it to which the System Console can communicate. If you start the System Console from Quartus with the compiled project already open, the System Console should auto-load that project for you. If you are connecting to multiple FPGAs on the same or different boards, then you would have to make sure you load the project for each target FPGA if they contain different projects within the System Console. For step 3, you want to select the IP to access and open the toolkit. Here, you should see all available Ethernet IP instances listed in the Instances column. Just highlight the Ethernet IP instance that you want to interact with and click on the Open Toolkit button. The software automatically recognizes the IP core type and opens the appropriate toolkit. For the final step 4, Now you have the toolkit open, you can start using it to debug and analyze your link. With it, you can access registers from almost all parts of the IP core. In our last section for this course, let's look at the Ethernet Toolkit user interface and how you can use it to get control and valuable information from your Ethernet IP core. This screen capture is the main Ethernet Toolkit view that you will see once it is open. At the top are the IP configuration and other information, the general commands, and the settings sections. From the middle down is the tabs section. This section changes depending on which of the three tabs you select. The three tabs are the status, the statistics counters, and the testing features tabs. The IP configuration and other information section lets you verify you have selected the correct IP and that it has been configured as you expected. You can check the number of channels in the IP and which IP components have been enabled, such as the MAC, the PCS, the auto negotiation and link training logic, and the RSFEC. The General Commands section has controls that can be used across different IP cores. Here you can enable and disable serial loopback for testing and link bringup, connecting the transmitter output back to the receiver input. You can click on buttons to reset the entire system, the I/O section, the transmit MAC and PCS, or the receive MAC and PCS. There is also an option you can click to indicate if you're using the example design. This enables sections of the toolkit UI that are associated with using the example design. In the settings section, if you have a multi-channel interface, you can select which of the IP channels you want to interact with, since each channel of the IP would have its own address space. The rest of the Ethernet Toolkit user interface is made up of information and controls for the active channel. It is broken up into three tabs. The first tab is the Status tab. Here are sections for link bringup, PCS status, PHY status, transmit and receive MAC settings, and auto negotiation and link training status. In the link bringup section, you will find options that you can use during link bringup to tune the analog settings of the buffer to improve signal integrity. Using the PMA Adaptation Select drop-down menu, you can choose between pre-configured analog buffer settings based on data rate and channel properties, for example, short reach versus long reach. You can choose internal adaptation if you're running in a serial loopback mode, or external adaptation if you're running a link connected to an external link partner. Here you can also verify the current status of the channel's adaptation logic. In the PCS and PHY status sections, you can see current values of the channel registers. These can be used to ensure the link is functioning correctly, helping you narrow down whether a non-functioning link is due to a PLL or channel issues. For the PHY, you can see if the PLL and CDR are locked to the incoming data or reference clock. If your channel has multiple lanes, you can see the information for each individual lane. For the PCS, you can see the transmit ready status and speed, and the receive alignment status, speed, and bit error rate information. To read the status registers, enable the tick boxes to turn on Read All Status. When you do this, the toolkit automatically reads the PCS and PHY registers at regular intervals and keeps the display updated. In the MAC settings section, you can read the register values of the receive and transmit MAC. These can be used to ensure correct core configuration and diagnose issues stemming from incorrect settings. Like the PCS and PHY section, you can enable automatic reading of the register maps as programmed by your IP configuration and your application. For the transmit MAC, you can view parameters such as the maximum transmit frame length, interpacket gap, source register, and the fault status. For the receive MAC, you can view parameters such as the maximum receive frame length, fault status, packet length checking, padding removal, and the start of frame delimiter checking. When you change to the Statistics Counters tab, you will then see the Example Design Packet Generator Settings, Transmit and Receive Statistics, and the PHY Status and Control sections. The Example Design Packet Generator Settings section is enabled only when you're using the example design and you have enabled the example design option in the General Commands section above. At the top of this section, you can turn on MAC Loopback mode, connecting the received MAC output directly to the transmit MAC input, forwarding any received packets back out the link. On the left side there, you can control the packet generator. Beyond clicking on the button to start and stop the generator, you can set the pattern mode and the number of packets to send. Note the display reports back to you the packet size range and the total number of packets sent. On the right side, you can use the example design to program specific source and destination addresses to use for your debugging session, so you can dynamically adjust MAC addresses based on the link partner. The Transmit and Receive Statistics section displays the current value of the IP core's statistical counters registers. So instead of checking the hardware for issues, now you have visibility into the actual packets you are sending and receiving, so you can investigate based on that. You get counts on packet types, packet sizes, and errors. You can start, stop, and reset the counters dynamically. The RSFEC section gives you access to the Reed-Solomon forward error correction logic registers for control and status information. Here you can dynamically enable and disable the FEC. You can inject errors into the lanes to investigate their recovery. And you can start, stop, and reset the RSFEC statistics counters as well. For example, you can see the number of corrected code words and uncorrected code words. This lets you see how well your system is handling the transmission and potentially noisy channels. The last tab in the UI is the Testing Features tab. On this tab are the Example Design PHY and Packet Generator Loopback Test, Read Register, and Write Register sections. The Example Design PHY and Packet Generator Loopback Test section requires the example design to be programmed into your hardware and the example design option enabled in the General Commands section. In this section, you can use the example design to run a predefined loopback test on your system and hardware. Use this test to perform a sanity check on your link. With one simple click, the example design will disable packet generation, bring up the link, check to see that the PHY and PCS are running, reset the statistics registers, enable packet generation again, and then check to see that the packets sent and received match. This test works with both internal and external loopback, but note that MAC loopback must be disabled before you can run this test. And finally, even with all the register visibility and functionality that we've seen in the Ethernet Toolkit, it is still possible that there are registers in the IP core which you want to access for your debug session that are simply not shown in the UI. If so, you can directly access them using the Write to and Read sections on the Testing Features tab. To use these, you must know and enter the exact 32-bit address of the register that you wish to read from or write to. This means several things. 1. If the documentation provides the register address in the form of a base and offset, you must manually calculate and enter the register's specific address. 2. You must know the purpose of the registered address that you enter, and you must know how to decode its content, as the tool does not provide this information. And 3. Some registers in the IP are listed as reserved or undefined. You should avoid accessing any of these, as the results of reading from or writing to them is unspecified. So this concludes our look at the Ethernet Toolkit. As you've seen from this training, the Ethernet Toolkit is easily enabled in your design or example design when you're configuring your Ethernet IP core. Once enabled, you have critical visibility and control into the operations being performed by the core through the core's register map. This visibility can be crucial when you're getting a link up and running or debugging potential issues. If you have further questions on either the Ethernet Toolkit or other Intel FPGA Ethernet solutions, please use the links on this page. Intel FPGA provides many self-help resources when you need design assistance. For example, there are web pages called landing pages dedicated to specific FPGA technology like transceivers, DSP, and high-speed serial protocols. There is also a community forum. And there are hundreds of training courses available just like this one. When you register for this training, a link was sent to you in your confirmation email that links to a short online survey. Please complete the survey to let us know what you think of this training and if you have any ways you think it can be improved. This concludes this online training. Again, my name is Marlon Price, and thank you for attending.